Moving on, hallucinations pose as a major challenge to our LLMs. Sometimes, what happens is when we make a query regarding certain information which was not present in the initial labeled data on which our model was pre trained, what our LLM does is for producing the answer, for producing its response, what it does is it tries to prepare a very convincing answer because our model is probabilistic in nature. So it tries to generate a very convincing answer. This is very risky in situations in the case of queries in which we have no domain knowledge. Like if we ask a question regarding MTH on which we have very less domain knowledge. So hallucination, if our model starts to hallucinate in that situation, so it's very risky, right? If you make a query like when did bears rule us? So the correct answer for this question would be no, they never ruled us. But instead of giving this as our answer, what it does is it gives out yes, they ruled us between 1920 and 1947. Now, if our domain knowledge, if our history knowledge is very weak, then we might consider this as our correct answer because very con- because it looks very convincing to our eyes. So our LLM is showing this behavior because the information regarding bears ruling us was never available to it because it does not exist. So instead of refusing to give an answer, it generates certain answers which are very convincing. So we tried to solve the above three challenges with the help of fine tuning. So we discussed about supervised fine tuning in which we update all our weights and biases. We take the initial weights and biases which it obtained after the stage of pre-training, and then this LLM is trained on a labeled data set. By labeled data set I mean prompts and their correct answers. These correct answers were initially prepared by humans so that our LLM learns to generate answers which are very suitable for humans. In the case of supervised fine tuning, our LLM updates all its weights and biases, all its billions, trillions of parameters, which is very computationally expensive. So we came up with parameter efficient fine tuning like LoRa and QLoRa. Basically, we used this expression, we freezed some weights and then used these low ranked matrices for fine tuning. So fine tuning solves our problem to a certain extent. Let's discuss one by one. The first challenge was of private data. Like our LLM has no access to that data set. Let's say we are making a query regarding a company named Amazon. So if we fine tune our LLM on documents, files, legal texts of Amazon, and then we make a query regarding that, then obviously it would be able to answer. The second thing is, the second challenge was knowledge cutoff date. Like the list of challenges which I presented is not exhaustive. There might be more also, but these were the major visible challenges that were faced by vanilla LLMs. For solving this problem of knowledge cutoff date, what we can do is we can regularly update our LLM. Like if we want to ask regarding today's weather, we can again fine tune our LLM on today's weather and then we can make a query. The third challenge was the problem of hallucination, right? So now if we give information of India's history from 100 BC to 2026, then obviously our LLM would be capable of handling queries which deal with history of India. So now if we make a query which we discussed above, when did bears rule us? So obviously it would give the correct answer, which was no, they never ruled us. Because India's history would include all the dynasties, all the rulers, emperors who ruled us. So our model would realize that there was no time frame in which bears actually ruled us. So the problem of hallucination will be solved. But the major problem with fine tuning, like it's true that fine tuning solves all these problems very convincingly. But the major challenge that it faces is computational cost. In the case of SFT, we are updating all of our weights. In the case of LoRa and QLoRa, even if we are taking A and B matrices which are low ranked, then also we are obviously multiplying matrices and all. So this certainly has some amount of computational cost. Another problem which fine tuning might lead to is the model might forget the initial skill and initial capabilities that it acquired after fine tune, which it acquired after pre-training. Let's say we pre-trained our model on English literature. Pre-training on English literature. Now we want our LLM to deal with French novels. So what we do is we fine tune our LLM on French models. We give a bunch of a historical drama or something to it, and now it fine tunes itself. So in some cases what might happen is, while fine tuning, it will obviously update all its weights. So now it might struggle to deal with English literature, like initially it was very comfortable because we pre-trained our model on English literature, but after fine-tuning on French novels, its capabilities are affected to deal with English literature. So is an this is an additional problem that fine-tuning leads to. And for applying fine-tuning, we need great technical expertise because we are updating all our weights and biases based on the labeled data that we provide, right? So if this labeled data has certain prompts and answers in greater concentration, then our LLM might be biased to those answers. Like if we fine tune our model on more positive sentiments compared to negative sentiments, then if we do a sentiment analysis task, there's a greater chance of it producing a positive sentiment. So these are the challenges which fine tuning brings to us. But yeah, it pretty much solves all the problems which our vanilla LLM faced. Thank you.